Here in this video, we will talk about Faraday's law of electromagnetic induction and their experiment. The phenomenon of electromagnetic induction was first discovered independently by Michael Faraday in 1831 and Joseph Henry in 1832. Faraday was the first to publish the result of his experiments. This world-known phenomenon is still charging and moving the world, without which we could not imagine our life. So let's talk about Faraday's experiment of electromagnetic induction in this video. For explaining Faraday's law of electromagnetic induction, let us take a simple coil, with which galvanometer is connected in series, and the permanent bar magnet on which N and S represents north and south pole of a bar magnet respectively. In this experiment, when we move bar magnet towards the coil, then indication of electric current can be seen clearly through the deflection of needle in the galvanometer. But when we stop moving bar magnet, then galvanometer does not show the indication of an electric current. Similarly, when we move bar magnet away from the coil, same phenomenon occurs. As we are moving the bar magnet away from the coil, there is an indication of electric current in the coil, which can be seen by the needle of a galvanometer. But this time, needle deflected in opposite direction. And when stop moving bar magnet, there is not any indication of an electric current. Now the question arises, what is happening? What causes the charges to flow in the coil? Is it because of motion of the magnet? So the answer is no. But how? Let's explore it. As we all know, bar magnet consists of a magnetic field lines emerging from north pole and entering in the south pole of a bar magnet. Therefore, when we move bar magnet towards the coil, magnetic field lines linking to the cross-section of the coil increases, or we can say that magnetic flux linking to the coil increases as magnet goes nearer to the coil. Because of that change in magnetic flux, that is, change in number of magnetic field lines passing through the cross-section of the coil, which induces EMF in the coil. As a result, electric current induces in the coil only if circuit is closed. But as we stop moving bar magnet, there is not any indication of electric current in the galvanometer. Similarly, when we start moving bar magnet away from the coil, this time magnetic field lines linking to a coil decreases or magnetic flux changes. Again, there is indication of electric current as long as we are moving bar magnet away from the coil. It's interesting to note that this time also induction of electric current stops as bar magnet stops moving. Here it is important to understand that induction of electric current occurs only when magnetic flux increases or decreases, or we can say that there should have to be change of magnetic flux. That is, change in number of magnetic field lines passing through the cross-section of the coil when magnet moves closer or away from the coil. It might have left you with the confusion that how could you believe that induction of electric current is because of change in magnetic flux and not because of motion of a magnet. To make it clear, let's do another experiment. This time, we will replace the magnet with another coil, which is connected in series with the battery in an open circuit. Now, when we closes the circuit, then just for that moment, the galvanometer which is connected to the adjacent coil shows indication of the induced current. Similar phenomenon occurs when we again opens the circuit. But this time, we don't have any magnet or motion of magnet. Then what's the cause of that instantaneous current which only induces for the moment when circuit closes or opens? Let's visualize this. When we closes the circuit, electric current takes some time to reach its highest value. Because of the electromagnetism, coil also starts acting like a bar magnet. Thus, magnetic field of a coil also changes from 0 to its highest value in a way that magnetic field lines of a coil starts linking to the cross section of the adjacent coil. Thus, the change of magnetic flux takes place in adjacent coil, which induces the electric current in the coil for the instant until current achieves its highest value of producing magnetic field. This change of magnetic flux takes place in very short period of time. So now it's clear that the electric current induces in a coil due to change in magnetic flux, not because of motion of the magnet. As in this case, there is not any motion involved, but still EMF induced in the adjacent coil, which is connected in series with the galvanometer. Similar thing happens when circuit is opened, and indication of electric current can be seen clearly in the galvanometer. This phenomenon of electromagnetic induction was first experienced by Michael Faraday and named as Faraday's first law of electromagnetic induction. That is, whenever there is a change in magnetic flux linking to a conductor, then electromotive force or EMF induces in a conductor. And if the circuit is closed, then this EMF produces current in the conductor. But Faraday's first law of electromagnetic induction only talks about the induced EMF and current. But it does not explain that what decides the magnitude of EMF and induced current in the conductor or a coil. Therefore, to answer this question, Faraday given second law of electromagnetic induction. So now let's try to understand Faraday's second law of electromagnetic induction. Now it's clear that change of magnetic flux induces current in the conductor. But magnitude of EMF induced and electric current depends upon the fact that how faster magnetic flux, that is, number of magnetic field lines passing through the cross section of the coil, increases or decreases. If we repeat the first experiment, but this time we'll move magnet more rapidly, which induces EMF and then current of higher magnitude will in the coil, which can be seen by the needle of a galvanometer. Now let's try to understand it with the help of mathematical expression, that is, magnitude of instantaneous EMF induced E is equal to the change of magnetic flux d phi over change in time dt. Or we can say that magnitude of EMF induced is directly proportional to the rate of change in magnetic flux. This phenomenon of electromagnetic induction is explained by Michael Faraday in his second law of electromagnetic induction, that is, the magnitude of EMF induced is directly proportional to the rate of change in magnetic flux. Here in this video, we have talked about how current induces in a conductor and what decides the magnitude of EMF induced in the conductor. But what about the direction of that induced current? So in the next video, we will talk about that how Lenz's law helps us to find the direction of induced current in the conductor. Thanks for watching, friends. If this video really helped you, please don't forget to like our video and subscribe to our channel. And also press the bell icon so that you will be notified whenever we upload a new video.